Hello, my name is Saban, and this is my mini C compiler project that I made for fun. And so basically what it is it's a compiler for a restricted subset of the C programming language, and it was written in C++ using LLVM's backend to do the actual compilation. And so it was mostly built to understand like how LLVM cooperates with a language front end and how industrial like level compilers are built. And so as you can see, like this is an example program that is compilable in mini C. And basically it's an add function, and there's a main function that just returns the result of the add function, a plus b. And this is the IR that comes out from the actual mini compiler. So for example, like you can see, like the add function is defined here. We have our SSA registers over here where it does the allocate for the variables, for the parameters, and it just does all these things. So overall, like in terms of features, it has a full lexer for C, so like it can lex, I guess, like the C programming languages, like keywords and all that. It has a parser for the subset specifically. Not everything exists, like structs don't exist, but most of like the core, like fundamental programming features are there. And so there's also a semantic analyzer, so it checks like type. It does type checking. It does like rules, like can you do this operation with these types. It also does like function parameter matching. So like, is there too many parameters in a function? Da 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 da. And there's also like the core C language features. So like there's the integer type. There's the while, if, and else statements. There's function declarations. So like int and void functions. You can have that as your return type, and you can also have parameters. There's no var args, but who even uses var args anyway? And so in terms of requirements, though, we have C++20. We need a GCC or Clang compiler. I tested on Linux. I haven't tested on Windows or Mac, so you could probably just use a virtual machine if it's really that bad. And LLVM, version 15 or newer recommended. And we have CMake, which is our build system here. And then there's just a build guide, you know. It's a regular CMake build process, pretty much. Um, so let's actually like demo this thing, right? So let's first talk about what we're compiling here. So we have a simple add function, and let's make this a little more spicy, right? Let's make sure that this compiles the addition of all three parameters. And then it just like does a loop with the result of the add function. So I don't want it to loop too much. So we're going to just make it loop 6 times, and it should be good. So what we do here is we run this code, and it runs the compiler. The compiler, it compiles this translation unit, right? And it generates, first of all, it prints out the file because we need to know what we're compiling. And then it generates the LLVM IR. And the IR, the intermediate representation, is basically what is the last step before turning into raw x86 or ARM or whatever AVR assembly, whatever platform you're on that's supported by LLVM. This is the last thing before it gets turned into basically machine code. So as you can see, it has like the add function. It has our variable promotions. So like as you can see, it promotes them using these alloc-a's. It stores them. And it does that for all three, and then it loads them, and then it adds them. It adds the first two, and then it adds the third one. So that's actually a feature. It's like recursive in a way. And then it returns the final result. And then we have our actual main function where it creates the queue variable here. It calls them, and then it also creates the I variable, and it jumps to the while loop and the while condition, break to the label while condition. And in while condition, we create a load for the variable I and the variable q, and then we compare the two to determine whether the loop should continue running. And so if that case is valid, then what we do is we break to the actual body itself. And if it's not true, then we jump to our while end where we have the return 0. And in the body itself, it's pretty straightforward. We just have like some updating stuff going on down here-ish, I think. And we also call the print function, which we'll call it a couple times. And so in order to actually like see this doing some, actual cool things, we want to copy this LLVM IR, and we want to run it through something called LLI. And LLI is a tool created by LLVM. And basically the idea here is that LLI can take IR generated by LLVM, and it can just in time compile it and then actually execute it. And so this allows us to see what's actually happening in the compiler without, skipping the steps and just jumping straight into x86. So now that we have pasted our program from here into there, we can actually see if it works, right? So we can go back and we can try to run this. And so to do that, we need to use the LLI command. And you will need LLVM to do this, right? So we go to LLI test/main.ll, which is our LLVM code, and it runs. So as we know, our main.c, first of all, it calls foo, it prints out foo because of this add function, and then we get our results, and then we have our while loop where we know it should run pretty much 1, 2, 3, 4, 5, 6 times, right? Or no, 5 times actually, I'm tripping. Yeah, 5 times. So it will do 1, 2, 3, 4, 5. So as you can see, the program is running. You can pause if you want to see exactly like what goes into it, but I can confirm for you that it does in fact work. Now let's get into the actual nitty-gritty internals of the compiler itself. So the first thing is the lexer, and so in the compiler itself, let's start from the main function, obviously, because the main function is where everything starts. So we have our file name. This should probably become part of the argv in the main function, so that is something to update in the future because hard-coded stuff is bad. And so we read the file using standard library, and then we pass those contents into the lexer. And the lexer is basically, for those that don't know, it takes your raw program code as a string and it chops it up into these little tokens so that we can understand like how the program is composed. And so that is the whole job of this lexer h and lexer cpp file. So we have a bunch of different kinds of tokens. We have like the parentheses, the braces, the slashes, yada yada yada, and we have our bang equal, greater equal, the drill of C tokens. We have our identifiers, strings, and numbers. We have our if else, for, while, return, int, shower, void, struct, break, continue. Not all of these features are implemented, but we do have lexer support for them. So while the lexer might not throw, it definitely will throw in later stages of compilation because it won't recognize those certain features like structs, breaking, whatever. Right. So in terms of how these are stored, we have our struct token, and this just stores a type, the value of the token as a string, and the line that it's stored on. This is good for error handling. And so in the actual lexer, we just have one huge function called lex, and what lex does is it's a huge switch statement on the actual tokens in the file. So we skip all the white space because white space is useless. Like you could have 100 tabs and it wouldn't be relevant to the compiler because the compiler just cares about the juice, not the space between the juice and the straw. So yeah, and then we get straight to the meat, right? We have our single character tokens, so like parentheses. There's no special like association where like you could have a parentheses and an equal and it'd be like something important. However, that does become an issue when you have like, for example, the not character, which is an exclamation point. If it is preceded, if an equals sign is preceded by that not character, then it becomes a not equal, and so we need to be able to differentiate. And so this check basically makes sure that that happens properly. And besides that, it's pretty straightforward. For identifiers, we just check if it's a character because that's how you check if it's a character. And for numbers, you just check if it's a number. If it's a string, you check for quotations. And if it's a char, you check for an actual apostrophe. And if you don't know what it is, then you throw an error and you crash and it does not compile, which is all this right here. And then it gets pushed back and then we return our tokens. And so overall, lexers aren't too hard to implement. It's just like certain edge cases, like, like the not equals or like the and or the bitwise and stuff like that. Yeah, so lexers are pretty cool. And then we got to do parsing. So parsing basically takes the list of tokens that we created in the lexer and it tries to organize them in a logical and coherent way for analysis and compilation. And so the way we do that is something called an AST. So the AST basically is like a bunch of nodes, right? So we can have like an operation like 2 plus 3 times 7. And what the AST is going to do is, first of all, Okay, actually, let's elaborate, right? Let's make this a block statement. So this is a technically valid C statement, right? And then we could just have like printf. I don't know, printf something, right? And so the idea is that we need to first of all organize these into a logical coherent data structure. So the way we do that is we create a list of statements. So for example, right now we have a block statement, right? This is stored in between two curly braces, so this is in a block statement. And the block statement itself, it has two internal statements, these two, right? The first one is an expression statement. And this expression statement, which we'll just call E, has some data inside of it, which can be stored in a node-like structure. So we have 2 plus 3 times 7. So 2 plus, and then we do this, 3 times 7. And so basically you can sort of like organize it in a tree. It's really interesting. There's a lot of good articles on how exactly it's done. And so for the actual nodes themselves, we have our expression nodes, which kind of depend on each other, which is like expression, literal, binary, unary, assignment, call, variable. These two are not implemented because I didn't have time. And they are all unified using standard variant, which is very useful because it allows you to write the visitor pattern in a very clean and modern C++ way, I guess. So yeah, very cool. And then each expression has a base class which just stores the line and the result type, and this is very useful for semantic analysis, but it usually starts as an initialized garbage value, which I just creatively named as 1319038 mini C unknown. And then we have our variable, literal, expressions, all the standard C expressions. And yeah, we have our expr variant, which is a bunch of unique pointers. And this is interesting because standard variant, it needs to know the size of the actual like class types it's holding. So you cannot use basically like you cannot use these classes without using unique pointer unless they're declared beforehand. And so in order to keep the code clean, yeah, you have to use unique pointer. And so that was something that took me like 2 days to figure out. Yeah, it was crazy. C++ standard library has its quirks, and yeah. Anyway, so yeah, these are the nodes. Pretty straightforward. So like for example, our assignment, we have our left-hand side, or right-hand side, or operation. So like the left-hand side would be where you're assigning to. The right-hand would be what you're assigning to the left-hand side. The operation would be the method of assignments, like times equals, does, and like stuff like that. Like you could do that sort of multiplicative thingy. Yeah, and then get literal type. This is some more C++ shenanigans. Obviously, like if you want to get the type of something, you have to create a visitor, and it's kind of unclean, but it's also, it is what it is, I guess. So yeah. And then, yeah, more of this get type stuff. Yeah, so like to get the result type. Oh yeah, and so like as I was talking, the unique pointer stuff, you have to be able to differentiate between unique pointers and non-unique pointers. So more C++ standard library thingies that just, are a pain to work out. And yeah, so those are the actual expression statements themselves. Now, obviously, C++, C is not an expression language, right? It is a language that starts at the level of declarations, and each declaration has its own statements, and then after those statements, you have your expressions. So how do we know about the statements? Because we're working from bottom up here. So we have our various types of statements over here. So we have print statement, return statement, variable declaration, expression statement, if else statement, while statement, block statement. And so you could just order these and sort of, yeah. So these are the different things. One thing about return statement is that I use standard optional because it can be empty. So that was just something that took a little brain power to realize. So like you can see here for if statements, we have a condition or body or else body, we have our blocks, and then we move on from statements to the next level, right? What encapsulates statements? Those are called declarations. And there are obviously many types of declarations, like struct declarations, function declarations, enum declarations, but for my purposes, we only have function declarations. And it is expandable, right? We use the variant what's it called, paradigm, I guess. And we do the same drill here. We have our name, return type. We just store all the useful info that we need here. And yeah, that's the AST nodes themselves. Now, how do we actually take what's chucked out of the Lexer and put it back into the AST node representation? Well, it starts all in here in get program, which is our top level function. So basically the way it works, right, is we get our program, we create a program which is just an alias for a standard vector of declarations, like functions basically. And so that means we're going to just parse a bunch of functions. And so what it does here is it goes through every single possible token in the file. And the program, we just push back a function declaration. Because at the end of the day, all we're trying to get are a bunch of function declarations, right? That is the definition of a translation unit in the context of this project. And so we just keep parsing function declarations until we can't. And if something goes wrong, then we just stop parsing. Now, this is not the best way of doing things, but it is what I did because I just want to focus on the actual LLVM side, which is coming up later in the video. And so let's go to parse function declaration. Right, so here. So basically, it's pretty self-explanatory in a way. Most of the parsing is just trying to predict what is coming next, and if it doesn't really match the rules that you want, then you just crash and exit and stop compiling. So like for example, we need to get the return type token, so we just advance, and that gives us a return type token. We want to know what line we're on? Great. Just take this and get the line that it's on. We want to know the return type, and then just get it from there. You want to know the name, advance another token, expect it, meaning it has to be there, otherwise we're going to absolutely go up in flames. And so we expect our name to be there, we expect our left parentheses to be there, and then we do our argument parsing. So we use a do while loop, which is like probably one of the first times I've ever used a do while loop in general. And so we store them in a vector, a function declaration, function arg, which is just a representation. It's a struct to represent function arguments. And we just go through every single argument in the function declaration. And after that, we close it off. We expect a right parentheses, and then we get the body of the function itself in the block statement. And we do some standard library magic. Yeah, this could probably crash, but like it's been fine so far. And after that, we return it, and that just goes back up here, and we just do it the same thing for the next function. And so for actual like statements, so like if we're in a block statement, which is usually the next level from function, right? We just keep parsing statements. And so to parse statements, we just peek on the next token. And based on what the next token is, we can usually determine what kind of statement we're looking at. So for example, if it's a type, right, we can usually infer that it is going to be a variable declaration. If it is an identifier, then we can infer that it might be a printf call or a general call itself, which it seems. That's weird. Why? Oh yeah, because it's an expression statement. Okay. Yeah, and so if it says if with an if statement, if it has a while, it's a while statement. If it's a left brace, we know we're opening up into a block statement. If it's a return, then we know it's a return statement. Otherwise, it's printf. So the thing about this compiler is that I made a distinction between printf and actual function calls, which I probably shouldn't have done, but it is something that I should probably fix in the future. And yeah. So in terms of like actually parsing, this is pretty boring. It's just like you advance, you get like the line info, and then it's just like expecting stuff, like, you know, I expect this character to be here, and then I want an expression, and then I expect that character to be there, and it just goes like that way for pretty much the whole thing. It's pretty self-explanatory as well, and this is what we like to call recursive descent, because it sort of like recurses when you do expressions, because an expression can be made up of more expressions. And so yeah, let's see. Oh yeah, error handling. Error handling is something that was kind of a weak part of this project. Like, I didn't put any line information or context, so like if you mess up, then you probably don't know where you messed up. But at the same time, this isn't an industrial compiler, so it doesn't really matter too much. This is more for learning. So after we move on from that, we are going to semantic analysis. And so semantic analysis is basically like parsing, but instead of predicting stuff, you check rules. So it's very recursive, just like parsing, right? It's composed pretty much in the same way. You're just going over the AST and trying to check whether certain rules are being met. So basically, at the highest level, right, we store a lot of information in this semantic analyzer because we want to know like what exists in the current context of the translation unit itself. So like for example, we have the current function that's being parsed, and this is very useful for like, let's see, what did I even use this for? Right, so if you have like a return statement and you want to know if you want to match the type between the return statement and the function, then you got to be able to know the function's return type. And so we store the current function that's being compiled because functions are a top level feature and there's no way that you're going to have a function inside a function. Also, we have our declared variables, and this gets overwritten with scoping and all that. And then we have our declared variable types. It should have probably been like a std string type, but I didn't do that, I guess. I don't know. Anyway. And we have our declared functions, and we have our current scope depth, because this is useful for like, you know, basically analyzing the stack itself. Like, because, you know, the C language, you can't access something after it's been popped from the stack. So, yeah. And then we also have like a grammar rules, like what can be added, what can be subtracted. In this case though, everything is an integer, so it doesn't really matter as much. But once you add like floats, cars, stuff like that, you need to be able to create a simple lookup table like that so that you can look up rules as needed. And so in terms of like actually doing analysis, it's pretty self-explanatory as well. You just need to be able to know what needs to be analyzed, and AI can help you with that, like finding what needs to be analyzed exactly so that you don't make a bad program. So like for example, let's look at our function declaration, right? Because this is the most verbose part of the semantic analyzer in my opinion. So the current function, we set that up, and then we need to make sure, first of all, that there's not a duplicate function, right? That's one of the first things. We want to make sure that there's no function that already exists like this. So we do that. Then we make sure that we know the actual types of the parameters, and we store them in the function prototype. And this is useful for when we call the function, because we want to be able to match the passed arguments types to the actual prototype of the function itself. And then we actually create the prototype here, by the way. And then we look at the parameter names. We make sure that there aren't duplicate parameter names. Another thing about semantic analysis, right? And then we insert the name, And then if we also check for a valid return type. If the type has not been declared, then it's not valid. So forget about it. And then after that, let's see. Yeah, we turn the body into a statement. We do analysis on the body itself, because we need to make sure that the actual function body is also valid in its own way. And then we just update it with rich information. We make sure that it has a return statement, right? Like another thing that semantic analyzers do for functions, I guess. And we make sure that if the function is non-void, that it makes a return. Now theoretically, like main function, it's a int, right? But like you don't need to put a return. That isn't really checked here because I don't care, pretty much. Yeah. So that is the declaration return type stuff. Yeah. Another interesting part of the semantic analyzer is like the block statements, because they're scoping, and scoping is cool. Because the thing about scopes, right, is like once you, let me just do this real quick, right? So like let's say you have like a block statement and you have like an int, right? Like int q equals 5. You need to make sure that q cannot be accessed outside of here, meaning after the block has ended. So the way we do that is with something called a scope depth. This is something I stole from crafting interpreters as well. Pretty much the whole front end is kind of like a mimicry, but anyway. And so, yeah, we do the analysis on the statements, obviously, and then we minus the scope depth. And so effectively what this does is so like when we make a variable, it stores its scope depth in the struct for the variable itself. As you can see, we can see its scope depth. Right now it's like infinite because -1 as a size t wraps around to like a gazillion, basically. And so here, the variables, they know their scope depth. And if the variables are too deep to be accessed, we filter them out using this. And then we erase them as well. So and if basically like what happens is you can't access them. And so it's kind of cool. Yeah, pretty much. Um, I thought it would be relatively hard to implement, but it actually was not too bad. But it is a very cool concept, and it just shows, I guess, like the beauty of the language in a way. So that is semantic analysis. Um, oh yeah, also like L values were interesting, and like the way that I handled variables. So one thing is like in LLVM, you need to be, or no, this is actually for IR, never mind. But L values. L values are important because like when you're assigning, the actual parser itself doesn't know that it's like an L value, but it can still create an expression on the left-hand side for that L value, kind of. Or no, that makes absolutely sense. So basically, like in C, the left-hand side can still be an expression, right? For example, like a pointer. If you do pointer arithmetic, then that would be an L value, but it's still an expression. Same thing applies for variables. However, we can't assign, like, for example, 1 to 1, right? Like, you can't set 1 equal to 2 or something like that. So how do we know that something is an L value? And so this is something that kind of confused me, but it turned out to be relatively simple in terms of implementation details. I think it was called is L value or is assignable. Is okay, yeah, is storable location. L values are just basically storable locations. And so basically just check if it's a variable. Now, you could probably expand this to like a pointer addition, or it could probably get more complex than this, but for now, the only type of L values that we have in this mini C compiler are AST variables. So, yeah. That was an interesting thing that kind of confused me, I guess. And now we get to the actually juicy part, which is the compiler. LLVM is a very huge beast. If we just go to the LLVM docs, let's see. So most of their documentation is created by Doxygen, which is like that thing that just looks at the comments and stuff. And yeah, it's pretty big. And there's not a lot of resources besides the LLVM beginner tutorial, which is obviously not enough for a small C compiler like this. So it was quite challenging to come up with the actual methods for compilation. And so AI definitely helped a lot in the finding of the exact functions that I needed. And so let's look at those functions in detail right now. So one of the first things, yeah. So one of the first things is that, so obviously we have our generate function. So this is all standard variant related, standard library stuff. So compile translation unit. So basically what we do here is we go through every single function declaration, right? So like when we generated our code, basically it looked at add and it defined add first, and then it went through main and then defined main and it generated the code for main. And it prints it out, and that's how we were able to access it here. Now in terms of actual generation, let's start at the function level because we're going to work our way top to bottom. So declaration gen, so this is dgen, declaration gen, it's just shorthand, it's a bad naming convention, but it is what it is. So we first get our type, and LLVM uses a very interesting naming convention. And so basically, let's go here, right? Int32 tie, int8 tie, void tie, right? So tie means type. They abbreviated it for some great reason. And so we store our default types in here. And so that's how we're able to know the type of the function itself. And then we do the same thing for our arguments, and then we do our LLVM function create. So this function just creates a function prototype and a declaration in the same thing. And so we just get the function, we do our return type, our arg type's false, meaning it's not a variadic function, so it means it can't take infinite arguments. And our function has external linkage, meaning it'll be non-static, I guess, if you want to look at it from a C perspective. Apologies. And it also takes our function descriptors, our function declaration's name, and the actual module, which stores all the code itself. And then it gives names to the arguments. It creates a basic block, which is kind of like the encapsulating feature for statements in LLVM. And we insert stuff, and then we just, oh yeah, and also like another thing is that the way that LLVM works is that it's a static or single storage assignment, something like that, SSA. And the idea is that you can't reassign to register. So what you need to do when you create a function, right, is that the parameters themselves are not actually considered variables in LLVM IR. They are just single static, whatever those are called. And so basically you need to promote them to an actual variable, and so in order to do that you need to create an alloc, which is basically a stack allocation. As you can see, it's like A is promoted as is turned into A as alloc A, meaning it's a stack variable, and we store it as a variable. And then we just generate the body, we do all the returning stuff, etc., etc. And LLVM, like, it's kind of self-explanatory as it goes. Like, for example, for creating a return statement, you just do create ret void if you don't want to return anything. Generating if-else statements and while statements is cool. There's a lot of like branching that goes on. Create condition break, basically like you can choose based on the value of an I1, which is just a boolean in LLVM, and it's kind of self-explanatory as well, but it's a little too verbose to explain well in a video like this one, and it just goes the same way for the rest of it. Another weird thing about LLVM's method for generating stuff is the naming conventions are kind of unusual. Like, for example, create f sub means create floating sub. Now, to an average programmer, this makes absolutely no sense, but so that was like one of the challenges that came along with making this program. Also, the same thing goes for like comparisons, right? Like icomp sgt. This means that the builder is basically trying to create a comparison between two integers that are signed and is doing a greater than comparison. This is what the GT means. So their naming convention is definitely an interesting one, and it was one of the challenges, like trying to understand what exactly those mean. Also, another challenge that I faced was the context that variables are being used in. So like, as you can see, we only have one AST node for like the evaluation of a variable and also like storing to it as well. So we need to be able to differentiate between storing and assignment. And so how do we do that in the context of LLVM? Because LLVM, when you do assignments, you need the pointer, but when you need to actually load the value itself, then you need to do something called a create load. And so in order to do that, I resorted to using a value flag. And this is kind of interesting. So the way it works is like, so if we go to assignment, right, it sets the value flag to false, meaning that we are not loading, we are trying to get the pointer. And so it's pretty scuffed in the way that it works, but it is something and it works. So I guess, yeah, it's a neat little tidbit. And so yeah, that's how the compiler itself is pretty much built. There's not much else. This is just mostly useless stuff that came from trying to mess around with variants. And that is pretty much it. Overall, it's been a pretty cool project, and I look forward to making more stuff like this. Thank you.